Hello everyone! Today we're going to be deriving equations of circular orbital motion using Newtonian mechanics. So imagine the following case where you have a mass, a large mass. Let's denote it by m1. This can be the sun, for instance, or a very massive star. And we have a much smaller mass, m2. This much smaller mass orbits around the first mass in a circular orbit. Our goal is to find some function or equation that tells us the position of the second mass in terms of time, so we can make predictions on its position in the future. Starting off, we can draw a free body diagram on the system. So we have the more massive objects and less massive objects. This force right here is the gravitational force, denoted by gmm over r squared, where we can replace these masses with the notation that we use. In this case, this equals to the centripetal force, or m2 v squared over r. This gives us the following equation: gm2 m1 over r squared equals m2 v squared over r. We can cancel 1 over r on both sides and cancel the second mass from both sides. This gives us gm1 over r equals v squared. We can rearrange for v by using square root on both sides, and we're left with gm1 over r. Now, to be entirely accurate, this is actually the length of the velocity vector. Why? Velocity is a vector, and in our system, velocity is always changing, because at this point in time, the velocity vector is pointing this way. But at a different time, the velocity vector is pointing in a different space. Its length, let's denote the length as L, is constant throughout the entire time, but its direction is always changing. That's why, to be entirely accurate, we have to write that the length of the velocity vector is equal to this thing right here. Yet this still doesn't really answer our question and doesn't really solve the problem, because all we get is the velocity of the object around the more massive object, but we don't really obtain a function which tells us its location. In this case, let's use spherical coordinates or polar coordinates and create a much more specific diagram of the system to be more clear. So this is our mass. This is at t equals 0. Let's denote the angle between the second mass and the first mass as theta. So this is the second mass, this is the first mass, and this is the second mass sometime in the future, assuming it's going this way. So we can rewrite v, the velocity, as omega r, where omega is the angular velocity. And the angular velocity is the rate of change of the angle, or the derivative of theta right here in respect to time. So we can use this equation right here and say that d theta over dt multiplied by r equals square root gm1 over r. We can bring the r to the other side, like so, and we're left with the first order differential equation. Now this differential equation is pretty easy, as it's separable and basically involves almost no tricky integration. Let's go ahead and solve this differential equation. We can bring dt to the other side, so you have d theta equals root gm1 over r cubed dt. And now we've separated the variables and we can integrate both sides, like this. D theta equals gm1 over r cubed dt. Apologize. There you go. So we have theta plus c, 1 equals root gm1 over r cubed. This is the solution to our differential equation. I forgot to put the t there. We can bring the constant to the other side. Theta equals gm1 over r cubed t, and label it a. So we have an equation, this is a function of time, that gives us the angle for the planet or for the lesser mass going around the larger mass as time goes on. The only thing left to do is to determine the constant. Looking at the equation and from physical, trying to interpret its physical meaning, we can set this constant to 0 because this constant refers to the initial, any initial angle that we have. So let's say we are starting at, in this example right here, we're at time t equals 0, theta equals 0, right? We can verify this is true by, if we set t equals 0, this term vanishes, and we're left with a equals theta. But theta is 0, that means a has to be 0. So if we're starting in our coordinate system where our lesser mass is directly above and theta equals 0, at time equals t 0, then our constant is 0. This leaves us with theta t equals root gm1 over r cubed multiplied by t. This equation is telling us the angle theta at a certain point time t. Let's verify this, or let's try to solve a problem with this. To verify this equation, let's apply it to the Earth-Sun system. Let's try to solve for the time it takes for the Earth to go around the Sun, which we already know to be 1 year, which we can verify this equation with. So, for the Earth to go around the Sun, our theta needs to be 2 pi, which is 360 degrees. This is 2 pi, and we're working in radians. So we put this in, so we have 2 pi equals root gm1 over r cubed t. T equals 2 pi over root gm1 over r cubed, like so. Now we can plug this into a calculator and see what we get for the value of t. Here we have our calculation. Our value for t is roughly 31.5 million seconds for the Earth to go around the Sun. We can verify that this is 1 year as such by dividing the number of seconds by this constant to get the number of years, which is approximately equal to 1 year. So we can see that our model is pretty accurate and the equation works pretty well. Now, as practice, you can use our previously derived equation to find the orbital period of the Moon or other planets in the solar system. But what is more important is that we attempt to use this equation to find the orbital period of a comet, for instance, the Halley's Comet, and we will quickly encounter issues. Now, if we use this formula to find orbital periods of different planets or moons, for instance, which have fairly circular orbits, we will find that the equation is pretty accurate. But if we try to use it on a comet or, for instance, any other object with a very elliptical orbit like this, our values that we will find are going to be very incorrect and very different from what is observed in reality. This is due to the limitation of our model, assuming a circular orbit. In future videos, we will attempt to derive equations for an elliptical orbit, which is much more closer to reality, using more advanced and accurate methods.